Hello, in today's video we're going to be talking about heating and cooling curves of different substances. In this case we're going to be talking about water, and in most of the heating and cooling curves that we're going to be dealing with, we're going to be talking about water. This is the heating and cooling curve of water. In this curve we're going to heat H2O from negative 40 degrees Celsius all the way up to 140 degrees Celsius. So in this case, we're going to go through a few different phase changes. We know that at negative 40 degrees Celsius, liquid water becomes solid. It's a frozen solid, so it's ice. So down at negative 40 degrees Celsius, we're going to be at ice. Once we reach 0 degrees Celsius, that 0 is something that you should have committed to memory, the ice is going to start to melt. Okay? Then we're going to get this range of our heating and cooling curve. This is the range of a mixture of solids and liquids. So down here, we have pure solid. This is just pure solid ice. In Q2, right here, we're going to be going from 0 degrees Celsius to 0 degrees Celsius. All we're doing is melting the ice. It's like you put an ice cube in liquid water and you see the ice cube start to melt. That's exactly what's going on here. We have a mixture of two phases, solids and liquids. Once all of that ice is melted, we can then raise the temperature again. So when we have this mixed phase, the temperature does not raise. We only raise or lower temperature when we're in a pure phase, one phase. Either the solid, in this case, we're in the liquid phase. We've seen this before. We've all dealt with liquid water at some point in our life. But once we get up to 100 degrees Celsius and we start to boil the water, the temperature doesn't change anymore. No matter, even though we're adding more and more energy into the system, the temperature of the water, the boiling water, does not change. The reason for that is because this is a mixed system. This is now liquid and gas. In mixed systems, your temperature does not change. If I were to ask you, you just started seeing bubbles bubbling in your water. You're making ramen noodles and your water is boiling a little bit. Not a feverish boil, but just a slight boil. And then you let that heat up for another 5 minutes and it's really, really boiling now. And if I were to ask you what's the temperature difference between those two different boiling, you have to say 0. They're the exact same temperature. A low boil is the same temperature as a high boil of pure water. Okay? So here we have a mixed phase. That's because there is this mixed phase. Some of the water, the H2O, is going from the liquid phase to the gaseous phase. And then once we've boiled off all of that liquid water and it's all gaseous, then we can raise the temperature. This is a pure gas phase. So why am I talking about this heating curve? Why do I have 5 different Qs? Well, each of these Qs is going to have a different equation that we use to solve for the heat that's absorbed by the water. Anytime we have a bend, a temperature change that's allowed for the system, we're going to be using our normal Q equation. Q equals mc delta T. Q equals mc delta T. Remember, heat absorbed or given off by the system is equal to the mass of the system times the specific heat of the system times the change in temperature of the system. So if I was looking at Q1 down here, I could use that equation. Q1 is equal to mc delta T. I could measure the mass of my water. I could figure out what the specific heat capacity is of water. I just looked that up in a table. And then I can multiply by the change in temperature. In this case, it would be 0 minus negative 40. So that is how much heat would be absorbed by the solid water for Q1. Now, Q2 is slightly different. There is no temperature change in Q2. So if I were to use the same equation, I would get mc delta T would be 0, and Q2 would be 0. But that is not the case. So anytime we have a flat bar on our heating or cooling curve, this is going to be considered a mixed phase situation. We have to use a different equation for our heat. In the heating and cooling of a solid liquid phase, we're going to be using Q is equal to the moles times delta H fusion. So this is if we're heating up ice. It's going to be heating. Okay. Now for cooling ice, If we're doing a cooling curve, this is a heating curve. If we're doing a cooling curve, we'd go down in the opposite direction of this curve. We could use also N is negative delta H fusion. This is for cooling. So the only difference between the heating and cooling equations is this negative sign. Okay. For fusion, fusion means this multiple phase, this solid liquid multi-phase. If we're heating it, it's positive delta H fusion. If we're cooling it, it's negative delta H fusion. So anytime we see this flat bar, we're going to be using N delta H fusion. So Q2 is going to be N delta H fusion. Great. Now we've taken our water, our solid liquid phase, and we've melted all of the solids. So we're at this point here. Next, we're going to raise the temperature of the water all the way up to 100 degrees Celsius. So we can go back to Q3 equaling mc delta T. We can use this equation. Now our m and our c do not change from this one, but the delta T goes from 100 minus 0. That's a different delta T. Okay. Once we're into the boiling phase, we have a mixed phase here. It's liquid and gas. In this phase, the temperature does not change. So for Q4, we're going to have to use N delta H. This was for solid liquid phase. For gas liquid phase, we're going to use N delta H vaporization. This is for heat. And N minus delta H vaporization for cooling. This is for the liquid-gas interface. This delta H vaporization, delta H fusion, we look up in a table or you're given it to you in a problem. Okay. So we have Q4 is N delta H, and it's going to be vaporization in this case. And then once we have all of the liquid water boiled, we're going to be able to raise the temperature of the gas. So we're going to go back up to Q5 is equaling mc delta T. So how does this work? How do we deal with these heating and cooling curves? We're going to have to talk about which phase we're in. If we're in a pure phase of only one type of phase, solid, liquid, or gas, we're going to be using the original equation of Q equals mc delta T. If we're in a mixed phase, solid liquid phase or liquid gas phase, we have to use a new equation. Q is equal to the moles times either delta H fusion if you're in the liquid solid phase, or delta H vaporization if you're in the liquid gas phase. So doing a heating curve of water going from -40 all the way to 140 degrees Celsius, there would be 5 different Qs that we could calculate. And if we wanted to figure out the total amount of heat absorbed, Q total is going to be equal to the sum of the individual Qs. So if I wanted to know the total, that's supposed to be a T, the total amount of heat absorbed by this H2O system going from -40 to 140, I would have to calculate the Q for each individual phase and then add them up and get Q total. And with that, that's all I want to say for the heating and cooling curves. We're going to talk a lot about this tomorrow in class. I just want to introduce you to which equations we use and where. Have a great night. I'll see you all tomorrow.